because we have to be on time at the end of the afternoon, otherwise the bus will be very upset, the bus driver. Okay, so please, the people in the back, take a seat. Welcome to this afternoon session. The first talk will be by Benjamin Seidel. Here is the title, please. Floor is yours.
So, hello, my name is Benjamin Seidel. I work at the University Observatory in Munich. I'm a PhD student there. I want to thank the organizers and also the other speakers because I think this nice little project I'm going to present to you fits right into the topic of what we discussed during the day. So that is very nice, thank you for that. To motivate what I'm about to show you, here is a little movie I made from a recent publication we published on high Z quenching in our cosmological simulations. So this is a main halo galaxy that quenches at around a redshift of 4. And what I want you to take away from these, maybe this has a little bit better contrast than the movie, what I want to take you to take away from this and what our main takeaways actually were in the publication is that the quenching of these galaxies is really, it really comes to pass due to a complex interplay of a lot of different things. You see a lot of things going on here. You see the cosmic web developing around the galaxy. You see the fairly isotropic flow with the characteristic slow inflow pocket to the lower right side. And then you see the eventual starburst just before quenching, and then the AGN feedback kicking in also and blowing a massive bubble into this cavity. So the main takeaway from this paper is that it's not only the feedback processes, but also the environment that really brings about these quenching processes, at least from the numerical perspective. To get a realistic environment to test this hypothesis in, I'm using the magneticum simulation because I'm working with people that created these simulations. And what you just saw was our high Z box, which is box 3, which combines a very, very nice box size with a fairly high resolution. I'm also featured in this work is going to be the box 4, which has the same resolution as box 3, but is not as tailored towards the high Z. And for extending the mass range towards groups and larger clusters, I'm also using the large cosmological box 4 with 640 megaparsec over H. So I'm going to focus mainly on accretion, which I think fits in nicely after lunch, so we're going to gain some mass here. The first point I want to make is that if we take the simplest possible model, so this is a relationship I derived from a Van den Bosch paper. This is based on simple extended Preschechter structure formation theory, and we measured the flows in our numerical simulations, so incorporating fully nonlinear dynamics. We get the flows fairly well, so the total flow is reproduced by this simple, these simple assumptions on how structures form. So we're not very off there, and if we add the outflows also, then we can see that we can see the effect of AGNs kicking in at larger radii, so the smaller halos can drive out the gas further, which is what we saw before also in the movie. The smaller halos can drive out gas further than the larger halos. But in general, the total inflow at least follows linear assumptions, so it's fairly simple. But the point I want to make here is, what about the geometry? You saw before this isotropic flow field with the low velocity pocket in the lower right. So this talk is really going to be focused on inflow geometry. And to sort of get a handle on that, in the simulations I have the advantage of being able to use full 3D information. I interpolate gas density and velocity mainly for this project on a spherical surface that's usually centered at 1 virial radius of the dark matter halo. And I can then provide really high definition, high resolution angular maps of the density and the velocity and the combination of the two, which is the flow field, which is going to be the main focus of this talk also. To extract the geometry, because you can look at these maps and they look nice and you can already see things going on there, I also perform, to get to the geometry, I perform a spherical harmonics decomposition of these maps, and this gives me a set of multiple coefficients. But as this is fairly abstract, and I wanted to test how well this works and how well this correlates with structure, I set up a very simple test case. So basically, I test how well these multiple coefficients correlate with filaments. I set up test maps that have just from 1 to 8 filaments basically in a coplanar arrangement, and then I can perform the decomposition and check how well these or what I get from the spherical harmonics decomposition. So I did that, and what I want to take away from this plot is basically that I can trace the number of connecting filaments, at least in this simple setup. I can trace them fairly well by just computing the maximum coefficient, basically. So if I have if the first coefficient is the maximum, then I have 1 filament, 2, and so on. So there's a direct correspondence between the maximal multipolar coefficient and the number of total filaments. To sort of check whether the geometry matters, I did various different setups. So here you can see a simple cross setup, basically with inflows from the poles and then from the sides also. And what you can see here in the red curve is that it reproduces what I get from the case with 4 coplanar filaments fairly well. So I can still trace different geometries with this setup. Okay, so this is nice to see. I can directly tie the number of filaments to my multiple coefficients. But I also wanted to quantify how isotropic the inflow is in total. So for that, I need a different parameter. And what I came up with, based on previous work on galaxy clusters, is computing an aspherical excess. So this is a parameter that is combined from the orders apart from the monopole, which is basically the isotropic component of the inflow, and summing up until the 9th order, which is kind of motivated from the histogram you saw before, also with the connectivity. So I wouldn't expect much more filaments than 8, and so I go to 8 filaments basically. So I truncate it at the 9th order. And what you can see here is that this quantity really doesn't it's not a direct tracer for connectivity, but it's a combination of connectivity and how the filaments are arranged basically. So if I set up 1 filament, it is the maximally aspherical case. If I have 0 filaments, obviously I'm at 0 because then all the power comes from the monopole. And if I attach more and more filaments, I add more and more infall directions, so I get more spherical again. So this parameter has this characteristic peak. And I also tested this for different thicknesses of filaments just to verify that this also works, because in a realistic setup I would not expect like a clean map like I showed you before in the test setups, but we have various different filament sizes. So the takeaway is that this asphericity parameter is that the more connected the cluster actually is, or the group or the halo in general actually is. So the more isotropic the infall basically. So this parameter gives me an estimate for how isotropic the gas is falling onto the halo. Cool, so now let's see some realistic maps. This is from actually the cluster sample from box 2b, but the galactic case is fairly similar. What you can see here is the velocity field and overlaid with density contours. So I've highlighted overdensities here. And I've highlighted like 2 different regions in both maps. So these are 2 different objects here at around 1 array. You can see here where the contour, the density contour overlaps with the velocity field. This is what I would call a filamentary region. And then I have also this diffuse outflow regions, basically where the density is very low and the material is moving out of the halo. To show you that this is not a hoax, I can also show that these are usually connected across different radii. So yeah, what you might have already noticed from the first map I showed you is that the inflow tends to be more organized into denser structures than the outflow. The outflow is more isotropically distributed, and this can be quantified now with the parameter introduced to you before. So what you can see here is basically from 12 to 15, 10 to the 12 to 10 to the 15 solar masses halo mass. This asphericity parameter, and you can see that it's consistently across the whole mass range. The inflow asphericity is higher than the outflow asphericity, which is nice to see because you can kind of get that visually, but you would like to extend that to larger samples, and then it's kind of hard to verify that visually. So main takeaway here is that outflow tends to be more isotropic than the inflow, which organizes into filaments, and this is consistent across the whole mass range. But now, since this conference is really focused on galaxies, I want to go to this sort of lower mass range. So what I did next is I computed this parameter for 1300 field galaxies from the high resolution box with solar masses above 10 to the 10, with stellar masses above 10 to the 10 solar masses, and traced the evolution across cosmic time. And what you can see here really nicely is that this parameter has actually an evolution across the different cosmic epochs. So we start out with fairly isotropic inflow. We saw that also before in the high-side quenching plot I showed you. Then we reach a peak and then a decline where the inflow becomes more isotropic again as the galactic fountain processes kick in. And yeah, we're just accreting more isotropically at low Z again. This is quite nice to see. Also, like a nice callback to what we saw before, that the halo received, so the early quenched halo received a fairly isotropic inflow in the time just before quenching. So this is nice to see here also come into practice again. And then also, because we saw this plot a couple of times already during this conference, this is in blue I plot the star formation density evolution across cosmic time in our box. So this is taken from the same simulation box, from the same sample of halos. And you can see that really the peak of star formation is in a phase where the inflow is still fairly isotropic. So there is a time delay between the peak in anisotropy of the infall and the star formation density peak. So yeah, I'm not implying a direct causal connection here, but it's quite interesting to see actually that we're getting this peak in a phase where the inflow is still fairly isotropic. So this is the main takeaway from these plots. Like we have this time evolution of this parameter. And now to deconvolve this even a little further, this is the same sample, just split up. This is work done by Silvio Fortuné, who is actually in the audience here. So what he does is he looks at these galaxies and classifies them based on their behavior to the star formation main sequence. And what was really nice to see in this plot was that every galaxy that undergoes some quenching process at some point during its evolution, so that falls off the main sequence at some point, has this characteristic peak in the asphericity, in the infall asphericity, as opposed to main sequence galaxies, which stay at fairly low, at fairly isotropic inflow, actually. But for further information, please check out Silvio's poster, which unfortunately is now not up anymore, but you can ask him directly about this. And one final point I want to make, I want to also connect this a bit to the dark matter, actually, to the dark matter field surrounding the halo. This is from work I've done with Lucas Valenzuela. So he studied the shape of dark matter halos. What you can see plotted on the y-axis is the shape of the dark matter halo, so the axis ratio from the shortest axis to longest axis ratio. So the higher this parameter is, the more spherical the halo is. And on the x-axis, I've plotted my inflow asphericity parameter, and you can see that although the correlation is quite weak because this is an integrated parameter and this is measured instantaneously, it's still nice to see that there is a correlation between the asphericity of the inflow, which lives in the same tidal field that the dark matter halo evolves in as well. So it makes sense that these parameters are correlated, but still, given that this is an integrated parameter across cosmic times, it's nice to see that it is kind of connected also. So yeah, I've already reached my conclusions here. So what I want you to take away is that environment can play a role in the quenching of galaxies in general, but especially high Z quenching. And while the total inflow follows linear predictions, we can trace the asphericities reliably with these multiple coefficient methods. There is this evolution in accretion flows, at least in our simulations that we find. So we have isotropic inflow at high Z, we have close to the peak or after the peak of star formation, we experience the most ordered infall, and at low Z we converge to isotropy again because the galaxies are pushing out a lot of gas and the flow becomes more isotropic again at late times. So I still have some time left, I think, because I haven't seen the 1 minute. 1 minute. So I just want to advertise other work I'm also involved in. So what I've shown you so far is just from magneticum simulations, which are random initial condition simulations. We're also working now on producing constrained simulations of the local universe, which reproduce directly counterparts of local clusters, local structures, and we're actually making good progress on that. So what I'm directly involved in is producing zoom-in initial conditions of local clusters that really are connected to the large-scale structure in the way they are supposed to be. So for we have good Fornax counterparts. We have a nice region for the Shapley region. We've discovered bridges that were found in the Rosita survey also. So we're really getting the large-scale structure down to a very realistic degree, and this could be quite interesting, I think, for studying the galaxy populations of local clusters, because the large-scale structure is reproduced fairly well in these constraint simulations. So if you are interested in comparing to some of these simulations that we are now running, please meet me at the conference dinner or at some point during the coffee break. Thank you.
Excellent. Thank you. Questions for Benjamin? Yes. Shall I?
Thanks. I think you mostly showed us analysis beyond the virial radius. Is that? So I was curious if you took it inside the halo and if
not yet, but that's on the list definitely. So yeah, we want to study that a little bit more. But really, the point is here that to show how these halos are connected to the outside, basically, because this is also the regime, as we had in the discussion before. This is also the regime where the specific feedback processes don't matter as much. So this should be the regime we should all be getting like correct. The simulations should converge on, so we look to the outside of the halo first. But it's definitely on my list.
You also emphasized visually that the filaments exist on different shells going out, so that they're real structures. It'd be interesting to automate that and apply it within the halo to kind of get at this debate, you know, how far do filaments survive?
I've started this process already, but it's not complete, unfortunately, so I can't show you anything on that.
More questions? There must be another microphone. Can I ask you about your zeta parameter?
Yes.
Where do you measure it? Where is the distance? Because I guess it probably changes with distance, right?
So everything I showed you is basically measured around the virial radius of the halo, so basically at one area.
Okay, so it's really accretion onto the halo.
Yes.
Okay, so but there is also then a time delay for that gas to get into the galaxy.
Yes, exactly.
Yeah.
That could also explain the time delay in the peak we see.
Interesting. Yes, another question there.
Hi, really nice stuff. I just wondered if you could comment on, there's a certain evolution between the relative size of a halo and the size of a filament feeding it, or filaments feeding it, and I wanted to know how that would affect your measures that you derive. Do you see something like that in the data? So
you mean like so you're wondering about whether there is an effect with basically the one virial radius surface of the halo scaling up with time, with the halo accreting more mass? Or
which grows, you know, extended pressure structure grows like m star of EPS. We can get that compared to the size of the filaments, which can also grow with time and so how would the change in the solid angle a filament covers, does that translate into the metrics that you derived? And how?
So two replies to that. So I showed before that I tested this for different filament sizes, and you can see that at least the evolution, of course, a larger filament will give you a lower asphericity in the metric I'm computing right now. So if your filament grows to a larger solid angle relative to the halo, and vice versa, if it shrinks relative to your virial surface, you will get a lower or higher asphericity based on that. But I've looked into, at least because I was also wondering this, we are computing this, let me go forward a bit into my back. Damn. It's a lot of things to click through. Sorry, just a minute. So at least what we looked at was how the median virial radii of these objects. So I was also worried about just scaling down basically by the halo scaling up, scaling down the filaments. But what you can see, because I'm always computing it at, so I'm computing this, all of these quantities are basically computed in co-moving space, and you can see that at least the median virial co-moving radius of the sample doesn't show a concrete evolution, so this peak is not caused by the halo scaling up from my interpretation at least. So I'm not downscaling my filaments by scaling up my halo. That's what I wanted to check with this blue curve, you can obviously see that the physical radius is growing, but it's just growing at the expansion rate of the expansion of the universe, so that's fine, I think, in my method.
Okay, thanks. I think we have to move on. Let's thank Benjamin again. The next speaker is Munira Hoosain, tracing H1 in galaxies in the cosmic web with ECO.
Hello everyone, my name is Munira Hoosain. I'm a PhD student at the University of Cape Town, supervised by Sarah Blythe and Rosalind Skelton. And today I'm going to be presenting some work that I've done in collaboration with several co-authors, including Katerina, on tracing neutral hydrogen gas in galaxies in cosmic web filaments with the ECO survey. And in case you're interested in reading the paper, here is a QR code that you can scan, and I'll have it at the end as well. So I thought I would start by re-emphasizing why filaments are important. Katerina gave a really amazing overview of them, but just in case you were thinking about lunch, filaments contain 40% of the mass content in the universe. And as mentioned in previous talks, filaments are important for supplying gas to galaxies to maintain their star formation. There have also been several observations that have suggested filaments have an effect on the stellar mass and color and star formation properties of galaxies, as well as several other properties like metallicity, etc., with galaxies tending to be higher in stellar mass close to filaments, redder and more quenched within the filament environment. However, when it comes to the gas content, things are not as clear. There has been some observational evidence that high mass galaxies are able to accrete gas from cosmic web filaments in Kleiner et al. 2017. However, on the other hand, there have been mixed results when it comes to looking at lower mass galaxies and simulations that suggest possible cosmic web stripping similar to ram pressure stripping, as well as cosmic web detachment that may reduce the gas content of galaxies within filaments. To study this, I'm using data from the ECO and Resolve surveys. These are low redshift surveys. Resolve is in red. It had its own additional H1 observations along with including alpha-alpha observations, and the environmental context of ECO survey provides an environmental surrounding to the Resolve survey, and I used the abaryonic mass complete sample from the ECO survey and used the spectroscopic redshifts and catalogs to map the filaments in 3 dimensions. These surveys also have group catalogs from Hutchins et al. 2023, which is the most recent. And you can see some of the other papers about these surveys here as well, which is useful so that we could study the effect of filaments while taking into account the group environment and all that comes with it. So to identify filaments, I used the discrete persistent structures extractor, or DISPERSE. It's a commonly used topology-based filament finding software. And because we had the group redshifts, we were able to correct for redshift space distortions and identify filaments in 3 dimensions. We also calculated the distance to filaments according to this little cartoon that is, I'm not going to try and fiddle with that, that you can see on the screen. And because galaxy groups tend to lie along filaments, we separate our sample into groups and singles so that we can try and isolate the effect of filaments on galaxy properties. Here is just a quick slide showing one of the slices in 2 dimensions of the 3-dimensional filaments. And you can see that the filaments trace the galaxy distribution quite nicely. In red, you have the nodes that Katerina talked about, which DISPERSE identifies, and galaxies are color-coded by their halo mass, by the group halo mass. What we found was, in agreement with most of the other papers, was that galaxies have stellar masses, have higher stellar masses close to filaments. We found this for both group and single galaxies. And when we looked at the red fraction, we first had to remove the underlying trend in stellar mass with distance to filaments, and to do this, we separated the sample into 4 mass bins. As per Canapan et al. 2013, the gas richness threshold in blue and the bimodality scale, which we have galaxies above it in orange, are important transitions in the gas refueling regimes of galaxies. Galaxies below the gas richness threshold, which we refer to as a low mass in this paper, are more likely to be accretion dominated, whereas high mass galaxies, which are the orange ones, are more likely to be quenched. And what we find in general is that group galaxies on the right are typically rarer than single galaxies across the board, across all the mass bins that we use. However, for single galaxies in blue, in the low mass bin, we find a small increase in the rate fraction close to filaments. When we looked at the gas content, we measured the fraction of gas-poor galaxies, which we defined as having a gas fraction of less than 10%. And we find that galaxies in groups are more gas-poor than their single counterparts as well. And we also did not find any statistically significant increase in the gas-poor fraction close to filaments, which you would expect to find with cosmic web stripping. And if you look at this plot, especially on the group side, you might be wondering there are lots of these like sharp increases at low distance to filaments for both the rate fraction and the gas content. And you might be thinking, oh, doesn't that mean that filaments are still having an effect on the groups? To test this, we looked at, we binned by halo mass, group halo mass, rather than stellar mass as well. And because group galaxies tend to lie along the filament and have their, and what we found was that these high mass halos were located at very low distances. So those are the purple-ish lines on this plot, the very high mass halos. And you can see that they are very gas poor compared to the other lower mass halos. And so what we found was that maybe it is more likely that these high mass halos are what's driving those sharp increases close to filaments rather than the filaments themselves. For the single galaxies, so these are galaxies that are not in any groups that were identified, we did find in the lowest mass, in the lowest halo mass bin, a slight, small, statistically significant increase for single galaxies in this very low mass halos, which we think may be possibly some evidence for cosmic web stripping, as these are very low mass halos. They might not be able to hold on to their gas as well as the larger halos, but there are also other explanations. So it is a bit of a question mark. I'm not sure how much time I have left. I feel like I went very fast. Oh, okay. I went through that very fast. So yes, just in summary, what we found was that galaxies close to filaments have higher stellar masses than galaxies further away from filaments. We also find a higher fraction of low mass red galaxies close to filaments. But overall, we find that groups have a much stronger effect on the reddening and reduction in gas content than the filaments themselves. And we do find this slightly higher fraction of gas-poor galaxies in low mass halos close to filaments that might possibly suggest some cosmic web stripping. There is some ongoing work by another student at UCT, Tilman Ogerslacher, who is studying the effect of cosmic web filaments at higher redshifts using data from the Laduma survey, which is a high redshift for H1 survey on the Meerkat telescope. And since I have a tiny little bit of extra time, the IAU's General Assembly is happening for the first time on the African continent in August later this year. So I'm hoping to see many of you there. And yeah, if you haven't registered and you would like to attend, the deadline is tomorrow. So you might want to get on that soon if you are planning to come to Cape Town. But yeah, I'm happy to take questions.
I'm glad to see that the speakers of this afternoon are really worried to miss the bus. So,
yeah, it's very interesting. Did you try to look at the gas properties of the blue and red galaxies separately?
I'm trying to think if we looked at the separating this, just separating the by the red.
The first turn red and then lose the gas or the other way around.
Yeah, so we mostly just looked at them by stellar mass, kind of because the stellar mass and the colors seem to be quite closely linked. I'm trying to remember if I did in earlier version look at them separately, but I can't remember, so I don't think so.
More questions?
Thank you, Munira. Nice talk. So just out of curiosity, so disperse traces the filaments based on the local overdensities, right? Based on the
Yes.
groups. So once you've removed those, how much of the filamentary structure is left? Does it not, well, disperse into non-filaments?
I'm trying, so yeah, it identifies these regions that are the highest density, which I also can't point to. The red nodes are the highest density regions, and then it traces the general density field. Yeah. So yeah, I did also in the appendix of the paper look at what happens if you remove these node areas, and we found that it had a very small effect, especially because we were already removing groups, which kind of included a lot of these node areas anyway.
More questions?
Hi, very nice. So you use a threshold of 10% in gas fraction to separate your gas rich and gas poor.
Yes.
This is potentially very high at high stellar masses and very low at low stellar masses. So have you thought of how this could affect your results?
Yes, so in an earlier version of this analysis, we also looked at H1 deficiency, and we found similar results. Yeah.
How do we detect cosmic web stripping?
Oh, that is a very difficult question. Yeah, because this is kind of what I was trying to do by looking at sort of the lowest halo masses and the single galaxies in these low mass halos, but we found very, very little gas removal. Yeah, so I suppose you might need to see more, either stronger gas removal in maybe a bigger sample, or it is just a very small effect.
Okay, if there isn't anything else, we can thank Munira again. Okay, next speaker is Daria Zakharova. Filaments in the Virgo cluster, atomic and molecular gas content in galaxies.
Hi, my name is Daria Zakharova, and today I would like to address two questions. Is a semi-analytical model which I use able to reproduce statistical properties of H1 and H2 content in galaxies within different environments, and what is the role of the filaments in gas evolution in galaxies within filaments? And I did this work not alone, but within Virgo filament collaboration, and here the list of the participants of this collaboration. Yeah, and to do my analysis, I take advantage of Virgo filament catalog, which was released in Castigliani 2022 work, which includes 7,000 galaxies in around 12 Vira radii around the Virgo cluster, and 400 of those galaxies across all the environments include CO or H1 available data to make analysis. Here is the distribution of galaxies and galaxies with CO and H1 sources. And I coupled this catalog with the Gaia semi-analytical model. I found 3 Virgo similar halos by mass. It's all that's available in simulated volume to make a comparison between observational and model data. And I need briefly to describe nomenclature which I will use in the next slide. So observational data based on the catalog was cutted by stellar mass completeness limit, which shown here And also I apply gas mass completeness limit, which was selected by I actually, and we use only, for gas analysis, we only use samples with stellar mass between 9 and 11 because to avoid any systematic problems with low mass galaxies, observation and really massive galaxies. And I couple this with Gaia data, and I use Gaia all sample, which was only cut by mass completeness limit, and went through mimicking the selection function to be comparable with observational data, but to obtain more comparable and data set, I also apply gas mass completeness limit and use only galaxies between 9 and 11 stellar mass. And this will be Gaia MOX setted, which comparable with observational data. And here my result, atomic molecular as a function of environment for cluster filaments and field galaxies. And we recover for all three environments a clear correlation between the mass of the atomic hydrogen versus stellar mass. And for galaxies which show H1 deficiency, so the galaxies which below main sequence for 0.5 dex, they demonstrate suppressed star formation rate. As for observational data, as for model data. And I measured the fraction of H1 deficient galaxies across all the environments for C2022 and Gaia MOX samples, and they are in really good agreement as total and for mass bins as shown in the bottom panel of the plot. So for atomic hydrogen, Gaia is able to reproduce the H1 deficiency in galaxies. Not only in statistical, just in number, Gaia is able to reproduce H1 deficiency distribution for galaxies in three environments for two mass bins. Moving to H2, we again recover a clear correlation between H2 and stellar mass for galaxies across all three environments. And for filaments and pure field galaxies, Gaia also goodly reproduce the fraction of H2 deficient galaxies, but there are some small inconsistency in for cluster galaxies, but it's probably related to problem with observational sample. And Gaia also able to reproduce a H2 deficiency distribution for massive galaxies across all the environments in a good agreement with Gaia, in good agreement with observational data. And to discuss the H1 versus H2 deficiency properties of galaxies within different environments, observations and the model recover a clear correlation between H1 and H2 deficiency, again across all the environments, and galaxies with deficient galaxies by gas demonstrate suppressed star formation. And cluster members have a largest fraction of H1 and H2 deficient galaxies in comparison with filaments and pure fields, and pure field galaxies have lowest fraction of H1 and H2 deficient galaxies simultaneously. And filaments galaxies demonstrate intermediate properties between cluster and pure field galaxies. As for low mass galaxy and for massive galaxies. And now I would like to discuss the role of the filaments in gas evolution in galaxies, and to do so, I, as my previous speaker told, I also would like to separate galaxies into filaments galaxies into two population galaxies who also live inside groups and in filaments, and those galaxies who are not participants of any group, so isolated galaxies, I will call them pure filaments galaxies. And here is the distribution of proportion of isolated galaxies and group of different size. And I would mention that this percentage depends on selection function. So it's based on the Gaia model, but it's applied with selection function, which overestimates the number of pure filaments galaxies because some of participants in the halo cannot be traced after selection function applied. And here is the result, the role of the filament at the fixed Halo mass. I compare H1 and H2 deficiency at fixed Halo mass for galaxies inside and outside filaments. And low mass end here corresponds to isolated galaxies, and inside and outside filaments, Gaia do not predict any difference in H1 and H2 deficiency. Also, as for massive halos, which corresponds to groups, we also do not recover any difference in H1 and H2 deficiency for galaxies inside and outside filaments. So for galaxies, at least for H1 and H2 deficiency, it's more important to be inside group or isolated galaxy, since we recover here a correlation between halo mass and deficiency parameter, rather than being or not being in filaments. And as a second test, similar to what was done by previous speaker, I also measure H1 and H2 deficiency as function of distance to filament axis. And galaxies in filaments indeed more H1 and H2 deficient near filament axis, but isolated galaxies in filaments do not demonstrate the same. So this dependency for filaments galaxies can be explained by contribution of group galaxies, which are demonstrated here, and galaxies inside rich groups demonstrate dependency of H1 and H2 deficiency with distance to filament. Yeah, and this is my conclusions of my work. Thank you.
Question from me.
Thanks very much. This might be a very naive question, and perhaps it's relevant for a few of the talks today. The difference that you just showed in the H1 and H2 deficiency between galaxies that were in groups versus by themselves, but in the filaments, could that be due to a difference in the mass of the filament itself within which group galaxies versus isolated galaxies live? And the corollary to that, maybe to everyone, is that something we can estimate observationally by doing these types of surveys? Can we estimate the mass or some estimate of the prominence of the filament itself?
Yeah, it should be difference, depends on how massive filaments appears, but it's for gas evolution of galaxies, it's second order effects.
I guess what I was going for, because a very massive filament would be more likely to have hot gas, whereas a less massive filament might not have as much hot gas, and ram pressure, stripping effect, etc., would be more prominent the more massive the filament.
Yeah, it's an interesting question, but I don't have answer for this.
Hi, this is super nice. I love it. I'm really glad to see somebody doing this and splitting groups and filaments. I guess my question is, do you think your results depend on the physics of Gaia and how Gaia implements environmental effects?
Yeah, of course. Gaia indeed do not include any filament-specific treatment. The only one thing which includes in Gaia as environmental, it is interaction with massive halos and assembly bias, which included in the merger trees. And so my conclusion really depends, my conclusion can be transformed that we don't see any assembly bias effect on gas evolution inside filaments. Yes, indeed.
When you calculate these average quantities, are you controlling for galaxy morphology?
No, my model does not include, semi-analytical model as usual do not provide the same morphological types as we do it in observation, so it will be really hard to compare. But I compared my H1 and H2 deficiency based on optical sizes and morphological type with my definition of H1 deficiency based on main sequence, and they pretty much agree.
I think if there aren't other questions, we can stop here. Thank Daria again. So the next speaker is Enrichetta Iodice, and you want also the title to be pronounced in Italian. Integral field spectroscopy of ultra-diffuse galaxies with MUSE, the LAVIS project, correct?
Thanks, Philip. Okay. Thank you very much. Yes, I like particularly the Italian style for LAVIS instead of Lewis. I'm a staff astronomer at the Observatory of Naples, and it's really a pleasure for me to show you a bunch of first results from this ESO-large program started in 2 years ago. I feel Nico. Okay. And we got more than 133 hours with MUSE to map a particular kind of galaxies, which are the ultra-diffuse galaxies in the Hydra 1 cluster. And this is the first homogeneous integral field spectroscopic survey of this kind of galaxies. Here there is the LAVIS team, which includes a lot of expert scientists in stellar kinematics, integral field spectroscopy, and stellar population analysis, a lot of 4 PhD students, several postdocs that are really joining this project. So first of all, which kind of galaxies are ultra-diffuse galaxies? Very diffuse and large systems were already known since 18th, but later in 2015, Piet van Dokkum named this kind of galaxies as ultra-diffuse. They are really, really faint, have a central surface brightness of 24 magnitude per arc second square, an effective radius larger than 1.5 kiloparsecs, and this size is comparable to the late-type bright galaxies, but have a stellar mass that is comparable to a typical stellar mass for dwarf galaxies. At time of the first study presented by Van Dokkum, he started to think how ultra-diffuse galaxies formed. So the idea was that this kind of galaxies, for some kind of a process, lost completely the gas supply at an early epoch. So they remain so large as late-type galaxies, but they do not form more stars. So they should appear red, quenched, metal poor, but should have should be dark matter dominated to survive to the cluster tides, because they were found in a cluster environment like coma. Since then, many processes have been, formation scenarios have been proposed to form UDGs. Here I would like to present many of them in one shot, and dividing them in internal processes, in short, some processes that push away the gas in the galaxies, and these kind of processes anyway predict some gas in the outskirts and a dwarf-like dark matter halo. Many other processes involve the gravitational interaction and mergings, so ultra-diffuse galaxies can form like the tidal UDGs from merging spiral galaxies, but also, as been mentioned before, UDGs might form from the gas clumps in room pressure stripped queues, but also UDGs can form from a tidal interaction between dwarf galaxies with a big bright galaxies. The properties are really different depending on such kind of processes. So we have dark matter free UDGs if you are if you have tidal phenomena, and you should also a moderate metallicity, some gas, but also gas-poor and dwarf-like dark matter halo if you form the UDGs in the process of this kind of tidal interaction. So, as you could already realize that from this scenario, we do not expect a single class of objects. So what about the observed properties? About colors, we have observed both blue and red UDGs. The blue UDGs are more distributed in the outskirts of the clusters. About the kinematics, we know we have, due to the low surface brightness nature, we have a really few measurements till now. It seems they have a low velocity dispersion. It's not measured a appreciable gradient for a stellar rotation. About the stellar population, Hold and metal poor system are observed, but also younger and star-forming UDGs. So the dark matter content of this object is one of the most debated issues, because it seems that UDGs that are dark matter dominated exist, but also dwarf-like dark matter halo, but also dark matter-free UDGs. And finally, in UDGs, there are also observed globular clusters, and in UDGs or coma, it seems that the specific frequency of globular cluster is larger with respect to the total luminosity of these galaxies. Which are the observables to discriminate between the several formation scenarios? First of all, we need deep images, in particular to detect them, but the spectroscopy is really the key measurements to address the stellar population, the dark matter content, and the stellar kinematics. And this is the context of Lewis. What we would like to do with the integral field spectroscopy of this sample of galaxies, we would like to measure the stellar kinematics to address the dark matter content, the stellar population to address the star formation history, and the evolutionary link with the dwarf galaxies, and also to detect to improve the detection of the globular clusters and have the spectroscopic specific frequency. Here there are the pillars of the Lewis project, in particular the postdoc Kyra Butita. She is leading the stellar kinematic task, the PhD Goran Dole and Marco Mirabile, which are PhD students in Naples and in Teramo, and they are leading the stellar population analysis and globular clusters. And then Mikhail Kerr and I, which are trying to push this project to some results. Here is the target, the Hydra 1 cluster. It is located in the south hemisphere. It's a really massive cluster, and this is the core. In the Hydra cluster, we discovered it exists a rich population of dwarf galaxies. More than 200 were new detection. These are the typical dwarfs, and this is one of the UDGs detected in this cluster. Here they are. This is the Lewis sample in red, and we have 22 UDGs plus 8 low surface brightness galaxies, which are in the transition regions between dwarf galaxies and the UDGs. Here is the plane where we typically, in the mu0 effective radius plane, where we typically find the UDGs, and these are the region where we found the dwarf galaxies, low surface brightness dwarfs, and extended dwarf galaxies. And in Lewis, we can map all these kind of galaxies. Why this is important? Because if UDGs, as it seems, are the faint end of the luminosity function of dwarf galaxies, we do not think it exists a different formation process with respect to dwarf. So it's really important to study the transition regions between the UDGs and the dwarf galaxies, just to map the formation pattern of the two classes of objects. We have already published a paper presenting the projects, and we used the 1 UDGs of the sample to test everything. Everything, I mean the data reduction with Muse, the sky subtraction, the necessary signal to noise to get the data, and we really push the Muse capability to such a low surface brightness level. And this is one of the UDG of the sample, and first of all, according to the Fabre-Jackson relation for low surface brightness galaxies, we really expect to measure such a low velocity dispersion. This is the integrated spectrum for these UDGs of the sample in the 1 array. The signal to noise is around 16 with the integration time of 6 hours of exposure. We measured the redshift, and we indeed measured a really low velocity dispersion. And just to give you an idea, these are the main absorption lines that we measured in the spectrum. We start mapping the 2-dimensional kinematics. This is the line of sight stellar velocity, where it seems that indeed there is no gradient. This is for many Levis data. We derived already the velocity dispersion, which is in this range of values. And compared to other literature data, we see a large scatter that is indeed intrinsic in many other points, and this is the velocity dispersion versus stellar mass. What about the stellar population? There is a huge spread in the metallicity, while they seems to be quite old. And this is a comparison of the Levis data with some other literature data, also for UDGs. We are start looking at some separation concerning the metallicity between the UDGs close to the core with respect to the UDGs more in the outskirts of the cluster. I mean, it seems that in the core there are more metal-rich UDGs with respect to those located in the outskirts, except for some outliers. This is a working in progress, so many more points are going to be added in this plot. How UDGs compare with dwarfs? Here we are. This is the dwarf galaxies observed with Muse from Hister and collaborators, and you see that the measurements are really consistent with the whole dwarf galaxies, and the range of metallicity is also the same. About the dynamical mass, this is the range for dynamical mass for local group dwarf galaxies, and we see that a comparable luminosity, we have dwarf-like dark matter halo for UDGs, but also we could have some objects which are more dark matter dominated. We have two special cases in the sample. The only UDGs of the sample which shows emission lines is UDG 6, and we have another object which is more interesting for this audience that I'm going to talk in a while. This is the UDG 6, which show, this is the Muse data, and this is the spectrum where we can detect the H beta, H alpha, and O3 emission lines. Here there is the distribution. And we are going to, this is the subject of a master's student. Moving to the southeast group of the cluster, here in this region of the cluster, it's known that there is ongoing ramp pressure stripping, in particular looking at the Wallaby data for NGC 3312 and NGC 3314. So look at this galaxy here. This is the optical deep VST image of these galaxies. This is a system of two galaxies in projection on top of each other, and the difference in redshift is more than 200 kilometers per second, and the foreground galaxy is the bluish one, is suffering indeed run pressure stripping. We have detected a huge system of stellar filaments, more than 50 kiloparsec from the center down here. And looking more in detail at the age of the filaments, this yellowish cloud is an ultra-diffuse galaxy. So the coincidence between the stellar filaments and the UDG triggered the idea that this might be formed from the gas clump of the run pressure stripping phenomena. And if the UDG formed from run pressure stripping, we might expect a younger age but a moderate metallicity. A while ago, we only can, from the optical images, we can only measure the colors, and we detected two candidates for globular clusters. So what happened with the news data? We discovered such a huge bright emission in the H alpha, which is absolutely spatially coincident with the UDGs. This is the spectrum around the H alpha that we can obtain from this tiny point, because all the rest is completely contaminated by the H alpha. I'm finished. And looking at the redshift, we can say that this is the redshift for 3314, using also the Mirka data. This is the redshift for the filaments, and this is the redshift for UDG32. So it seems that the structure is absolutely coincidence, not only spatially, but also in the UDG should be really there. And what about the dual globular clusters? They are intracluster globular clusters. So look, according to the redshift, they are not associated with the galaxies. What about the star formation history? These are really preliminary results, but the preliminary measurement seems to be in the direction that it is quite young and has a higher metallicity with respect to the other UDGs. And here there are my conclusions for the Hydra 1 UDG sample. In particular, I want to focus on the open questions that we would like to address in a while. Thank you very much.
Questions for Enriqueta there? Very nice work. I was just curious, maybe I'm terrible, but I've seen you saw a plot of velocity dispersion versus stellar mass,
yes,
which shows basically no correlation. And my guess would be then this velocity dispersion are probably not for a dynamically relaxed structure, so they might indicate something about tidal features.
This one.
Yes.
This one. So the scatter is really high. First of all, this point, yellow and red, here I put a label saying intermediate or unconstrained, because for this object, we know that this range of signal to noise are not enough to have an unbiased value of the velocity dispersion. What I'm saying is that we are measuring a larger velocity dispersion. So I would not consider more these points. But indeed, the scatter here is high. And you are right. We don't know if they follow a correlation or not. I would say that some objects follow the correlation, but some other not. And if you remember the formation scenarios for UDGs, the observed property do not fit with a single formation scenario. So in one sample, we can have UDG formed in a tidal processes and some other not. So I would not put all of them on this relation.
Great talk, and I have to ask about the UDG in the tail. Do you have also data that allows you to constrain the ages along the filaments, and if that matches with the age that you get for this
This is in
UDG?
the line to do. This is in the line to do, yes. Yeah.
Thank you.
Thank you very much. Did I understand correctly? You said in the galaxy that you think might have formed in the tail, you detected a few globular clusters around that galaxy as well. Do we expect galaxies, I mean, even if we believe, and it seems plausible, that galaxies can form out of ram pressure stripped tails, do you think we can form globular clusters out of ram pressure stripped tails? Because that seems extreme.
No, indeed. Indeed. Yeah. This was one of the main issues before having musing data. Because because from deep imaging, we detected these point sources that have colors consistent to be globular clusters. Okay. Using Muse data, we got the redshift. And the two globular clusters do not have a redshift consistent with the UDGs, but rather with the cluster. So they probably are intra-cluster globular cluster, but not associated to the UDG. So this is a point in favor of the formation in the ram pressure stripping scenario.
Is it still true on average that UDGs have more globular clusters than expected based on their stellar mass or halo mass? That used to be.
We have both in the measurement.
Actually, my question was asked about globular clusters. You mentioned about globular clusters in this system, but how about in general? That's my question. So how many, you sort of said that, so what's the fraction of UDGs you observed which have large number of globular clusters?
Yeah, I would say 20% in Hydra. 20% of UDGs has a bunch of globular clusters. Right now, most of them consistent with their total luminosity. We have two cases in which the specific frequency seems to be higher. But this is still need to be confirmed with the Muse spectrum.
Thank you. Very interesting.
Hey, Riquetta, this is really nice. Just staying on this one, time scales. What's the time scale of the stripping, and do you have enough time to form a UDG? Because we are talking probably about less than 100 million years.
Yeah, this is a good question. We should really think about this, because right now we are trying to see if we are really seeing these kind of objects, and then think about if we have to, for sure, make some comparisons with simulations. Yes, correct.
We thank Enriqueta again. So the last speaker of this session, well, before the coffee break, is Paola Merluzzi, ram pressure stripped radio tails detected in the dynamical active environment of the Shapley supercluster.
First, many thanks to the organizer letting me present this work, and then many thanks to the colleagues who contributed to the work. The first case of late-type galaxy experiencing ram pressure stripping has been detected in radio continuum. From the observational side, in the last 10 years, visual spectroscopy took the lion's share in interpreting ram pressure stripping mechanism. But now, thanks to the new instrumentation, radio is back. We undertook recently a project to make a census of the radio sources across the Shapley supercluster, the well-known most massive and dynamical active structure in the local universe. It encompasses 25 clusters, and here I show a galaxy density map of the supercluster. In the central region, the Shapley Supercluster Survey provides a rich multi-wavelength data set, and we started from this region to analyze the radio images. Here I show the radio coverage of the supercluster, which is already multi-frequency. More data are on the way. The region is covered by Rosita and will be completely mapped by the spectroscopic survey chances with foremost. In the central region, we identified and studied in detail 4 RAM pressure stripped galaxies as ascertained by the integral field spectroscopy and hydrodynamical simulation. 3 of them, those here, also present prominent radio tails. Here I show in red the radio continuum contours from Meerkat at 1.28 gigahertz, and in cyan the H-alpha contours from integral field spectroscopy. The radio and the H-alpha tails share the same location with respect to the disk, indicated by the air band image from BST. The 2 objects on the left has radio and H-alpha tails which are similar in length. The 2 objects in the upper panels both present a truncation in the radio contours and H-alpha contours with respect to the disk. The galaxies are observed at different wavelengths. This is an example for the galaxy in the bottom right panel, and this for another galaxy. So now there are a lot of questions, but a couple of questions are how RAM pressure stripping RAM pressure affects the relativistic electrons out of the disk, and which is the environment of the tailed galaxies. We use the multi-frequency data set, which enable us to disentangle between the galaxy and the tails. Actually, we resolved the galaxy and the inner tail and an external tail. And we can obtain the spectral fits in these 2 regions, which show a steepening of the spectral index in the external tail, and from the break frequency, the radiative age also show an aging of the electrons in the external tails. For this galaxy, the in-band spectral index from Meerkat also show a steepening of the spectral index in the inner tail, while for the other galaxy, the in-band spectral index is confined on the galaxy disk, but is capable to trace the star formation across the disk. In fact, the spectral index steepens in a post-starburst region, as determined by the optical spectra, from the optical spectra, and it flattens in a starburst region. The third galaxy also presents a clear aging in the tail, and the in-band spectral index trace this parameter from Meerkat, trace this parameter out to the external tail. So we put everything together. In projection, the non-thermal component and the ionized gas present similar morphology and orientation. Considering the consistencies among the epoch of the onset of stripping that we obtained from the simulations, the age of the youngest stellar population from the optical spectra, and the age of the radiating electrons in the tail from the synchrotron spectra, we can say that these galaxies are, in these galaxies, both the radio and the H-alpha tails are affected by run pressure stripping, by run pressure with similar efficiency. Now, the electrons in the tail can originate from the galaxy disk, displaced together with the baryonic matter, and so we expect a consistent aging of electron in the tail, or they can be related to the in situ star formation in the tail and also reaccelerated by shock excitation. What's happened in our galaxy? In this galaxy, we have the radio, the morphology of the two tails that is consistent, and we detect an aging of the relativistic electrons in the tail. So we say that the radio tail is fooled by relativistic electrons from the disk, as observed in coma by Chen and collaborators. This other galaxy, also we have a similarity in the radio-emitting plasma and ionized gas tail. We found an aging in either tails of the electrons, but a modest aging of the relativistic electrons in the outer tail. We know from the optical spectra that the star formation ionized the gas in the tail, and so we propose for this case that the radio tail is still fooled by the relativistic electrons from the disk, but there is a contribution in the tail from in situ star formation. The third galaxy, in this galaxy, the radio tail is much more extended than the H-alpha tail. We observe a modest aging of the relativistic electrons in the tail, and we know that the shock excitation play a role in the tail. So the tail is fooled by relativistic electrons, but shock excitation reaccelerate the electrons in the tail. So we have an answer to the first question. What about the second question? All the galaxies are found in environments with evidence of cluster-cluster interactions, both pre-existing and occurring. Because of time, so this is the answer, but because of time, I concentrate to tell you the story of this galaxy, which is set in the core of the supercluster, is a member of a poor cluster. And this is the radio continuum observations of the region. In this map from Meerkat at 1.28 gigahertz, we are able to detect a low brightness intracluster diffuse emission that connect the cluster 3562 to the group. And this emission that is 1 megaparsec long has the shape of an arc and a bridge. And these features are consistent with the scenario proposed in 2004 by Finogenov and collaborators, with an off-axis interaction between the cluster and the group passing north to the cluster and falling into the cluster core. And here we have our galaxy with its tail unambiguously oriented, which is a proof, let's say a piece of evidence that this, what we are observing, is a run pressure stripping triggered by cluster-cluster interaction. And I leave you with this impressive fresco, which, yes, I am biased, but seems to me a pictorial representation of the Shapley supercluster core as seen by a galaxy. Thank you.
to think about this a bit.
Hi. I wonder if you have time to compare, if you have compared yet the radioluminosity with the star formation rate for those galaxies with long radio tails, and if you find them in agreement with other estimate of star formation rate or not.
Okay. The three galaxies, for one of these galaxies, we have found in the disk, a star formation which can be related to the run pressure stripping. And with the diagnostic diagrams, we know if the gas is photoionized or shock ionized in the tail, but we don't have the resolution to trace the population, let's say the age of the star formation in the tail.
I was meaning the integrated star formation rate, because radio continuum is a very good proxy for star formation rate.
Yes, you mean for the radio continuum?
Yes,
no,
this class of, okay.
We didn't.
You were showing that one of the tails was mostly powered, reaccelerated by star formation, while another one by shocks. If you have ideas on what can cause this difference in galaxies?
Yeah, thank you for the question. There are two possible explanations. The first one is that the sensitivity, the H alpha sensitivity can be much lower than what is needed to trace all the tail. The other one is that the time scale of the star formation. Let's see, the radio tail trace the old star formation, the H alpha, the young star formation, and it is easier to follow the old star formation than the youngest one. This is also observed in a sample of local galaxies.
Yeah, indeed, absolutely. Thank you.
Just to follow up on the last question, you showed these three cases of potential origin of the acceleration of the electrons in the tails. Do we already know from a statistical point of view the frequency of the three processes?
Okay. So, for what I have read at present, there are not so many studies that are addressing these things. There are some work from Vollmer, and there are some work for Gavazzi, and there are the work of Chen, Lal, etc. And in all this different work, you have a different, let's say, conclusion. What I think is that everything may happen, can happen, will happen sooner or later. So I don't think that, I don't feel that one explanation could be more realistic than another one.
Last question.
I was wondering whether your target have AGNs. If yes, is there a possibility that some radio emission is originated from AGN activity?
Okay. So since we have an integral field spectroscopy, we know if there is in principle, we know if there is an AGN or not. In these three galaxies, there is not an AGN. In this one, which has not yet, because it was observed only by ASCAP, in this one there is the AGN.
Okay, let's thank Paola again first.
You're welcome. Thank you.
Okay.
Just one thing, so that you know, tomorrow morning we begin 20 minutes later, 9:20. So excellent. All the program tomorrow is shifted by 20 minutes, okay? So tonight we can drink a bit more.
We reconvene at 20 past.